Next, exercise 17. So let us first see what is given in the exercise. We are given a set G whose elements are formal symbols that look like this, where I can take these two values 0 and 1 and J can take these n values starting from 0 and ending at n minus 1, where n is some fixed integer greater than 2. Okay, and we assume that two such formal symbols are equal if and only if these corresponding numbers are equal. Further, these relations are also true. So let us first decipher this part. These symbols are formal symbols in the sense that they have the form of a product of two powers of ordinary real numbers. I mean, they are of this form, say 2 to the power I times 3 to the power j. But one should understand that clearly this is not a real number. These x and y by themselves, they have no separate meaning. They are only parts of this whole formal symbol. This is called a formal symbol because it has the form of this type of product. That's all. Okay. Now, two formal symbols like that are considered to be equal. That is, we are defining equality only when they are exactly the same. That is, the number above x, they are the same, and the numbers above y, they are also the same. Otherwise, they are considered to be different. These relations, however, at this stage, we cannot make sense of them. We will come back to this. Okay, so this much we have understood. What these things mean, we will come back to it. Now let us see what we are required to do. In part A, we have been asked to find the form of this product again as such a formal symbol. Okay, whatever that means, we have to do that. Now, using that product as binary operation, we will then have to prove in part B that our set of formal symbols G is a non-abelian group of order 2n. And in part C, after proving that this is a group, it will have its own center, which we already know as the set of all elements in G that commute with all the elements of G. We know what the center of a group is. If n is odd, then we have to show that the center has only the identity element. Otherwise, when n is even, we have to prove that the center has something else also besides identity. So we will make sense of these things, but let's just read this part also. This group is known as the dihedral group. A geometric realization of this group is obtained as follows. Let y be a rotation of the Euclidean plane about the origin through an angle 2 pi divided by n. Okay, so for example, if n is 3, because the smallest value of n can be 3, is 3. So then the angle is 2 pi divided by 3. That means what? 2 pi by 3 radian means what? 2 pi radians is 180 degree divided by 3. So that is 60 degrees. So that means when n is 3, y represents rotation of the Euclidean plane, means ordinary plane that you know in plane Euclidean geometry, the plane that you come across, that is the Euclidean plane. So rotation of that plane about the origin will be the center of rotation through an angle 60 degree. Okay, and x is the reflection about the vertical axis. That means you consider the y-axis, because there is an origin, there will be an x-axis and a y-axis on the plane that have been chosen already. Then about the y-axis you reflect the plane, so that is another operation. Then G is the group of motions of the plane generated by y and x. Okay, to understand this part we actually have to do quite a few things if you really want to understand what they mean. So let us start the solution. Note that we still haven't made sense of these relations, that we will do in the solution. Before solving the exercise, let's make some things clear. The relations x square equal to y to the power n equal to e and xy equal to y inverse x are meaningless unless we know what the symbols x, y and e mean. Okay, because you see the only symbols we have right now with us are these formal symbols, where I and j have so and so variations. You know how their values can be chosen. I can take the value of either 0 or 1 and j accordingly takes some other values. And we have also said that in this notation the total symbol has a meaning. What is its meaning? It's a formal symbol that is an element of G. However, we have said that without saying anything else, x and y by themselves have no meaning. So if we don't know what they represent or what they mean, then clearly we don't know these relations also what they mean. So to rectify this problem, we are going to actually define these symbols in terms of the formal symbols. We define x to be the formal symbol x1 y0, okay, y to be the formal symbol x0 y1. Note that I can take the values 0 and 1. So we have chosen 1 here, 0 here, no problem. J can take the values any of these, one of these values. Okay, now since n is greater than 2, so the minimum value of n is 3, and when n is 3, then this number is 2, so we can always choose j equal to 1. Okay, even in the smallest possible case where we have only 3 numbers 0, 1 and 2, only 3 choices for j, so 1 is always available for us. And we are defining the symbol e to be the formal symbol x0, y0. Okay, now what are we supposed to do? Now what are we required to do? We are required to define a binary operation on G. This is part A. Defining that binary operation is part A, where the author has said he has asked us to find the form of the product. So essentially he is asking us to define the binary operation that turns G into a non-abelian group of order 2n such that in this group the relations are true with the above definitions of x, y and e. Okay, if x, y and e mean these formal symbols, then after defining the binary operation and after showing that the set G forms a group under it with all the requirements, then in that group these relations should be shown to be true. That's what we are required to do. So let us start our solution from part A. In part A, we are now required to define the binary operation on G. So that means we will be operating on two such formal symbols. So for this and x to the power k, let me just call it x to the power k, although it's not power, but because the form is like that, y to the power l. They belong to G, we define their product to be again a formal symbol of that form, where now we have I plus k, where I am writing a suffix 1 with the plus sign. What is that special plus I will say afterwards. And y to the power L plus 2 plus, that is, this is another type of plus, minus 1 to the power k times j. Now I have to say what that 1 plus and 2 plus are, where this is the remainder one gets on dividing the ordinary integer I plus k by 2, and this is the remainder one gets when L plus minus 1 to the power u times j is divided by n. Okay. Now, does it make sense? Let us see. I and k, each one of them is either 0 or 1. The point is that they are after all integers. So, I plus k is also an integer. Now, if you divide I plus k by 2, then what are the possible remainders? The remainder can either be 0, in which case there is a proper division, that is I plus k is divisible by 2, or the remainder is 1. So that means this I 1 plus k is either 0 or 1. So it can be chosen as the number above x, because in the formal symbols we are considering the first number can either be 0 or 1. Like that, since L, oh, I have written u here, sorry, this is k. L, k and j, these are all integers. Depending on whether, see, k originally cannot be negative, because k itself is also either 0 or 1. When k is 0, then minus 1 to the power k is 1. When k is 1, then this power is minus 1. So that means here we are having actually either L plus j or L minus j. In any case, this is again an integer, and we can divide that integer by our integer n, and when you do that, the remainder you get is any one of these numbers, because the remainder has to be non-negative, it has to be an integer, and it has to be less than n, less than the divisor. So, and these are the numbers that we can take in place of the second number. So the definition we have given actually gives us again an element in G, again such a formal symbol. And because two such formal symbols are equal if and only the corresponding numbers are equal, so you can see that this operation is well defined. Instead of saying all these things here, I am just simply going to write, it's clear that the above operation is well defined. We can, however, add separately this observation. Note that I1 plus k belongs to this set, and L2 plus minus 1 to the power k times j belongs to this set. This is one of the reasons, I mean, because of this, our final result of this operation is again an element in G, and from the criterion for equality of two such formal symbols, we clearly see that this operation is well defined. That is, if you take two equal symbols, then the operation is not affected. I mean, in its place, if you consider another formal symbol which is equal to this, then you get the same result, and that is because in that formal symbol the same numbers I and j should appear. So actually you are not considering anything new. This is not a case like the case of a coset. Say in a group you have a subgroup K, and you take two elements of the group x and y, and you form the cosets kx and ky, and they happen to be equal. This can happen even when x and y are not equal. In fact, this will happen precisely when x y inverse is an element in K. And as far as a general subgroup K is concerned, we know that it may have elements other than the identity element. So x y inverse can be one such element. So if you form the coset by x and you also form the coset by y, for which this relation is true, then the corresponding cosets will be equal. So a single coset can have two different looking representations. That is not the case here. If you consider another such formal symbol which happens to be equal to this one, then I and I prime should be exactly equal. They should be the same integer, and so are j and j prime. So each formal symbol actually has exactly one representation. So that's why in this case the operation is trivially well defined. Okay, so this is our operation, and since this operation is well defined and the result belongs to G, so this is a binary operation on G. So now we start part B. So in part A we have been asked to find the form of the product. We have done that. This is our alpha, and this is our beta. Okay, we have seen in part A above that the operation defined on G is well defined. So G is closed under the operation. Okay, now next thing, of course, we have to verify associative law. Now you will see that despite having this somewhat complicated looking convoluted definition, associative law is still true. Let xiyj xkyl. To verify associative law, we need three elements: x, u, y, v be three elements in G. Then I will need it will be better if I do the calculation in the middle, then it will look better and clearer. Okay, let us first calculate this product. First we apply the definition here. Let this one sit outside. This one will give us k1 plus u. Okay, I have to be careful. For y, if you go back to the definition, you will see that the order of the things is like this. First v, then minus 1 to the power u, then l. Okay, it comes from that side, from right side to left side. V 2 plus minus 1 to the power u times l. I hope I am clear. Okay, now we have to carefully calculate this one. So for this one, y to the power, here also we will start from this, then minus 1 to the power this times j. So that means v2 plus minus 1 to the power u l 2 plus minus 1 to the power k plus u, k1 plus u times j. Okay, now we are going to perform some steps whose justification we will give afterwards. In place of this, I am writing this. Why? Are they equal? In fact, they are equal. Exactly why they are equal, that we have to write. Okay, let's first do the calculation. Then y to the power, this becomes v plus minus 1 to the power u. Okay, let us do it in one more step. First, let us write this plus 2. This 1 plus can be made ordinary plus, that is minus 1 to the power k plus u j. That also has to be justified. Okay, so all these things are there. Now we can take, in spite of having this strange looking operation, this operation is actually nothing but addition modulo n, if one really thinks about it. Minus 1 to the power u can be taken common out. V plus minus 1 to the power u, inside we will have L plus minus 1 to the power, this is 2 plus, okay, minus 1 to the power k times j. Okay, now we try to see that this Fermat symbol is actually this product. I plus k y to the power, okay, so with I we are having k, and this one is L plus minus 1 to the power k times j. This thing, and x to the power u y to the power v. This step, however, we can verify now itself. According to the definition, these two numbers, for them we have to take 1 plus, that is equal to this, I 1 plus k 1 plus u. So that part of the definition gives us this. Fine. Then what about this one? What about the power of y, the exponent of y? For that you have to come from this side. V plus minus 1 to the power u times this. V plus minus 1 to the power u times this. Okay, so according to the definition, this indeed is this product. And now again you apply the definition here inside the bracket. Then you get times x to the power k y to the power l. Let's verify this one also. I 1 plus k l 2 plus minus 1 to the power k times j. Yes, now it's time for us to write justifications for the steps which are not obvious. Now we justify some of the above steps. We seem to have used the fact that this integer and this integer are equal. Note that but before I write anything, let's recall one fact about congruences. Suppose you have an integer 12, say, and you are dividing the integer by 3. Okay, if you divide it by 3, then what will be the remainder? In this case the division is complete division, so let's just divide it by 5, say. So if we divide by 5, then the remainder is 2. Okay, and from this equation we can write 12 is congruent to 2 modulo 5. That means when we are having an integer and we are inside a modulo environment where the modulus is some given integer, then we can replace the integer by the remainder it leaves when we divide the integer by the modulus. That is, instead of 12 we can write 2. So that means in place of 12, suppose you have I plus k, and in place of 5 you have n. Okay, then you can replace this integer by the remainder it leaves when divided by n. But by the definition of this 1 plus, that remainder is precisely this. Mod n. Okay, so the fact here is that we have this type of congruence and we are going to use this now. These integers themselves are not, they may not be equal, but they are congruent to each other, mod n. Note that we first write this one. I plus k 1 plus u is congruent to, if you think of this as the remainder when you divide this ordinary sum by, say, n. Now our modulus is n. In this case the modulus is 2. If we divide this by 2, then by definition the remainder is this, because here we have 1 plus. This congruence is modulo 2, so we are going to ultimately write mod 2. Just like that, this one also, in its place you can write ordinary I plus k, because this I plus k leaves this remainder when divided by 2. And we know that ordinary addition of integers is associative, so this is equal to I plus k plus u, and that is congruent to the remainder, and in its place we can write again the remainder mod 2. Okay, so that means this integer and this integer are congruent to each other modulo 2, but they are remainders when we divide something by 2. So each one of them is a non-negative integer and each one of them is less than 2, because that's how remainders when we divide by 2 behave, or that's what they are. since I plus k plus u and I plus k plus u are both non-negative integers less than 2, the above congruences imply that they actually have to be equal, because when we have this congruent to this mod 2, what does that mean? It means that their difference is divisible by 2, but each one of them is less than 2, so their difference, the size of the difference, the numerical value of the difference will be also less than 2. Okay, so in that case 2 can divide the difference only when the difference is 0, that is only when the integers are equal. The situation is like this. Say you have this, no? This can take the value 0 or 1, this can also take the value 0 or 1. Now 0 is not congruent to 1 mod 2. 0 is congruent to 0 mod 2 and 1 is congruent to 1 mod 2. So that's why they have to be equal in order to be congruent if they are non-negative and both of them are less than 2. So congruences imply I plus k plus u is equal to I plus k plus u. So clearly we can replace. Now just like that we try to show that these two things are equal, this one and this one, but before that we have to also say how are we able to replace this 1 plus by ordinary addition. Also k1 plus u is congruent to k plus u mod 2. This we have already seen. This implies either this and this are both even or they are both odd. Why? Because this congruence tells us that their difference is divisible by 2. So it cannot be the case that one of them is even and the other one is odd, because in that case the difference will be odd and no odd integer is divisible by 2. So either both of them should be even or both of them should be odd. Hence, if both of them are even, then these powers are both equal to 1 because the exponents are even. If both of them are odd, then the powers are both equal to -1. In any case, the powers are equal. So hence -1 to the power k1 plus u is equal to minus 1 to the power k plus u. So k1 plus u and k plus u are not equal, they are just congruent, but these two powers of minus 1, they are equal. So we have replaced this by this, that is justified. And now we have to prove that these two, I mean here this is justified, here we haven't done anything else, we just replaced this one with this one. Now we have to show that this integer is equal to this integer, then our justification will be over. Finally, and here also the argument is like this. But we have to carefully see what we are writing. Let's keep this part. Finally, we have, let's start with this. v2 plus minus 1 to the power u l 2 plus minus 1 to the power k plus u times j. Okay, first we carefully get rid of the two pluses. So this is congruent to E, and now our modulus is n. The 2 plus inside stays for now L, but the 2 plus outside becomes ordinary plus. Now the inside 2 plus also becomes ordinary plus. Now from here you can of course take minus 1 to the power u common out. So this is equal to v plus minus 1 to the power u times L plus minus 1 to the power k times j. Okay, and now we will bring the two pluses back. V plus minus 1 to the power u times L 2 plus minus 1 to the power k times j, and that is congruent to finally v2 plus minus 1 to the power u. Don't lose track of what we are doing. We are freely able to write ordinary pluses in place of two pluses because the 2 plus operation gives us the remainder when we divide an integer by, such a sum by n, and we are working with congruence modulo n. So that's why we are able to do it. K times j mod n. Then again same, since on one hand we have this v2 plus minus 1 to the power u times L 2 plus minus 1 to the power k plus u times j, and on the other hand we have this. Are both non-negative integers less than n and let me put some ink. The above congruences imply that these two integers are actually equal. V plus minus 1 to the power u times L plus minus 1 to the power j is equal to okay. So we have completed justifying all the steps in our previous calculation. So the operation defined on G is associative. So the biggest hurdle is over. There are the other axioms also, but which we will only mention is associative. One can verify that the formal symbol E, which we have defined to be this one, acts as an identity element. Okay, one can verify means of course you please verify it. Okay, and then we have this also, the inverses, the element or the formal symbol. Let's just write element because they are elements also in G. The element x0 yn minus j acts as an inverse of x0 yj belonging to G, and the element x1 yj, that is x1 yj belonging to G acts as an inverse of itself. Okay, one can verify these things. Hence, G is a group under the operation defined. It's easy to see that order of G is equal to 2n. Order of G is 2n. For that we need not have waited this long, because we already had G in the beginning, and also we had a criterion for deciding when two formal symbols are equal. So there itself we could have just concluded that there are 2n elements, and the elements are just this. One, etc. x1 y0, x1 y1, x1 yn minus 1. So here you have n elements. In the second row also you have n elements. So in total there are 2n elements. And according to the definition of equality of formal symbols, these are all distinct elements, because the numbers appearing above this x and y, they are all different. Okay. Now we need to show that G is non-abelian. Now let us calculate the product xy, where we know what x and y mean. So the product is this: x1 y0, x0 y1. So let us straight away apply the definition. 1 plus 1 0, y to the power 1 plus 2 minus 1 to the power 0 times 0. Okay, and this becomes equal to what? When we add 1 and 0 we get 1. Dividing 1 by 2, the remainder is 1 itself. So that means this is x1. This term becomes 0, so 1 plus 0 is 0. Dividing that 1 by n, or again the remainder we get is 1. So xy actually is equal to this formal symbol. But what shall we get if we calculate yx? Yx is this x0, y1, x1, y0. Okay, now let us calculate this product. So this product is equal to 0, 1 plus 1, y, 0, 2 plus minus 1 to the power 1 times 1. So this becomes x1 because 1 plus 0 plus 1 is 1, which when you divide by 2 you get the remainder 1. And what we get here 0 minus 1 is minus 1. Okay, you get minus 1, and when you divide minus 1 by n, what is the remainder? Let's see that carefully. When we divide minus 1 by n, then the remainder is this. 1 times n, not 1 times n, minus 1 times n, plus n minus 1. You look at this equation. Minus 1 is our integer which we are dividing by n. So quotient times divisor plus remainder. The condition is that the remainder should satisfy these inequalities, which this n minus 1 is satisfying. So n minus 1 is the remainder. Okay. And these two things are actually not equal. Note that x1 y1 is not equal to x1 yn minus 1 because n is greater than 2. What does the criterion for equality say? It says that the corresponding numbers should be exactly equal. The first numbers are equal, they are both 1. The second numbers will be equal only when n is equal to 2, because here then we will have 2 minus 1. But it's given that n is greater than 2, so that cannot happen. So they are not equal. Thus, xy is not equal to yx. This proves that G is non-abelian. We are not done yet. Of course, even the part B is still not finished. That is because those relations are still there. But this I leave to you. I leave to you to verify that those relations are actually true. Now that we have the binary operation and also the meanings of x, y and e, one can verify that x square equal to y to the power n is equal to e, and xy is equal to y inverse x. So now part B is over. Then we move to part C. Here we want to decide the type of elements we have in the center of G. So let us take any element in the center of G. Let xi, yj be any element in the center of G. If you find this word somewhat weird looking, it's because I am not writing it in American English where people write CENTER. Okay, we are writing CENTRE. You can of course write whichever you want in the center of G. Then for any element x, k, y, l belonging to G, we have, being in a central element means it will commute with every element, so we must have this. Equal to x, k, y, l, x, I, y, j. Now this last equation, if you perform the operations and then take into account the equality using the criterion for equality of two such formal symbols, then you will get this. This is equivalent to this congruence, and the congruence is this. Minus 1 to the power k minus 1 times j is congruent to minus 1 to the power I minus 1 times L mod n. Okay, this has to be true if this is true, and conversely also if this is true, then this congruence has to be true. Now in this congruence you should understand that I and j are somewhat fixed. I mean, this is any element in the center but some fixed element, whereas k and l you can put any values, any permissible values of k and l, because this has to be true for every such element in G. This commuting property should be true for any k and l. If you keep I and j fixed and you keep varying k and l, then also this should be true because this is a central element. So that's what we are going to do. We are now going to put special values of k and l and see what we get from this congruence. Choosing so what is our first set of choices? So first we choose k equal to 0 and l equal to 1, and l equal to 1 we get, if we put k equal to 0 here, then we will have 1 minus 1, so the left hand side is 0. But if we put l equal to 1, then the right hand side becomes minus 1 to the power I is congruent to 1 mod n, because this will be congruent to 0 mod n. So that means minus 1 to the power I is congruent to 1 mod n. Now note that I of course can take only one of the two values, 0 and 1. When I is 1, then you have minus 1 congruent to 1 mod n, but that means what? N divides 2, because n will then divide the difference of 1 and minus 1, which is either 2 or minus 2. In any case, n divides 2. This however is not possible because n is given to be greater than 2. So how can it divide 2? So that's why I cannot be 1, I must be equal to 0. We directly write this implies I is equal to 0. So we know that in this central element I has to be equal to 0, it cannot be 1. Now we look for ways of determining j, and for that we are again going to choose special values of k and l, and the next choice is k is 1 and l is 0. Next, choosing k equal to 1 and l equal to 0, we get okay. Now if k is 1 and L is 0 means this part will be 0, the right hand side will be 0, and the left hand side will be minus 2, that is minus 2j is congruent to 0 mod n. Minus 2j congruent to 0 mod n, that means n divides minus 2j, so n will also divide 2j, which implies (2j) is equal to nm for some non-negative integer m. Non-negative integer because j is non-negative, n is positive, 2 is positive, so m also has to be non-negative. Okay, now two cases arise. If n is odd, then n must divide j. If n is odd, then you see n is dividing 2j. If n is odd, then 2 and n will be relatively prime, so n has to then divide j, and in that case, and so j has to be equal to 0, because you see, since this formal symbol is after all an element in G, and the possible values of j are these. Among these integers, only 0 is divisible by n. The other integers are all less than n and positive, so none of them is divisible by n. Only this one is divisible by n. So since j takes only these values, so j can be only 0. Thus, in this case, the only central element is I is 0. I is 0 that we found before. I mean, we have found I equal to 0 here. I has to be equal to 0 in a central element, but now j is also equal to 0. So when n is odd, then only the identity is there in the center. So G has only this trivial center. Okay. Next, if n is even, then if n is even, then what can we say from this equation? Then j is equal to n divided by 2 times m, because n now is even, so this n by 2 is a positive integer, times m. Since j is less than m, we must have m less than 2. If m is greater than or equal to 2, then multiplying on both sides by n by 2, what do you get? This is equal to n, but this is j. So in that case you will get the contradictory fact that j is greater than or equal to n, but it's given that j is less than n. So m has to be less than 2, but m is a non-negative integer, see. So the only possibilities are m is either 0 or 1. Thus, m is either equal to 0 or m is equal to 1. Accordingly, the two possible central elements are, when m is 0, then j is also 0, and in that case we get this element back. And when m is 1, then j is n by 2. This is a new situation. So in this case we get the element so when n is even, the center has this element besides the identity element. In this case it's bigger than the trivial root. So this completes the solution. The geometric realization of this dihedral group you can understand. In the geometry, we have y representing the rotation through an angle 360 divided by n, or 2 pi radians divided by n. Now when you compose two such rotations, say what is the meaning of y square? The meaning of y square is performing two such rotations one after another. So if you perform that rotation n times, what will you get? You get a rotation through an angle 2 pi radians or an angle 360 degree, that is a full rotation, and you bring all the points back to their original position, which is like doing nothing. So y to the power n is equal to identity. X is the reflection about the vertical axis. If you reflect once and then again you reflect, then you come back to you bring the plane back to its original state. So x square is equal to identity. So in this geometric interpretation, the relation is automatically verified. One can also make sense of this. And in the geometric interpretation, note that the binary operation is already available to us. It's actually composition of mappings. We will talk more about this later on when we, in the next section, we come across the idea of isomorphism, homomorphism, that thing. According to that, this dihedral group and this group, see, they are actually totally different. No, here x is a formal symbol, y is also a formal symbol in this exercise. Here, however, y is a rotation, x is a reflection. So they are entirely different things. But in spite of that difference, the groups, if you really look at them, behave exactly similarly. That similarity is pinned down in the definition of an isomorphism, two groups being isomorphic. So we will see those things later on. So let's now see the next exercise. Let G be a group in which for some integer n greater than 1, we have this relation. A b whole to the power n is equal to a to the power n times b to the power n for all a and b, for all elements a and b in G. Show that there are two parts. This set the set of all nth powers of group elements is a normal subgroup of G. And in part B we have one less value of the exponent. Another subset this is also a normal subgroup. Of G. Okay. So let us see the solution. First we need to show that this set is a subgroup. So let x and y be any two elements in G, so that we can consider two elements x to the power n and y to the power n in Gn. Then x to the power n times y to the power n inverse. If we can show that this is again in Gn, then by the criterion for a non-empty subset to be a subgroup of a group, our Gn will be a subgroup. Or if you want, you can show it in two parts. First, say you show that the product of any two elements in Gn is again in Gn, and then you show that the inverse of an element in Gn is again in Gn. Or you can do like this at once. Okay, now in place of this we can write this. Why? Because here we are using one of the rules of exponent. That is because ultimately this power will become y to the power n times minus 1. So that you can also write like this by the rule of exponent. And by the hypothesis that we are given, you think of x in place of a, and in place of b you think y inverse. Then you get this, which is after all again an nth power of some group element, namely this group element x y inverse. So this belongs to Gn. Thus this is a subgroup of G. Next we want to prove that the subgroup is normal. So let G belonging to G. Let G belong to G. Then G x to the power n G inverse. If we can show that this again belongs to Gn, then our job is done. But we have already seen this in other places, that this can be written like this. And if you really want to, and this clearly belongs to Gn, want to know, we want some reference for this property, then see the solution. To exercise 30 in this set of exercises itself. Thus Gn is normal in G. So part A is pretty straightforward actually, I must say. Then part B. For part B also we choose two elements in G, so that two elements in G n minus 1 can be chosen. Then you look at this calculation. Okay, you look at this product using associative law and rules of exponent. this is x to the power n, y to the power n, and by our hypothesis we can write it as xy to the power n. Note one more thing, that since it's given that n is greater than 1, so no, that we need not there is no need to think about the fact that n minus 1 is actually a positive integer. Negative powers of group elements also are permissible, so fine. So the rules of exponent and our hypothesis has brought us here. Now you think of this thing, this type of product. When you write this, the real meaning of this, say n is equal to 2, the smallest possible value of n, then it is xy xy. So do you see that if you don't think about the outermost x and y, inside you have yx. If you have xy whole cube, then you have xy xy xy. If you think about this part only, then you have yx yx, that means yx square y, and this will actually continue. In general, for this thing you can write x yx to the power n minus 1 times y. If you want, you can prove this by induction on n, that can also be done, to be absolutely sure that what the pattern we are seeing, it continues. I am just simply writing the step without any further explanation. Now we are in a group where the situation is so that we can apply the cancellation laws. Thus, by the cancellation laws, we have x to the power n minus 1 times y to the power n minus 1 is equal to yx to the power n minus 1. So you see that these are two arbitrary elements in G n minus 1, and their product is again such an element, because yx again is an element in G, it's the n minus 1th power. So this belongs to G n minus 1. Also, if you take the inverse of this element, then by one of the rules of exponents, this is the n minus 1th power of x inverse, which again belongs to G n minus 1. Thus, G n minus 1 is a subgroup of G, showing that its normal is almost singular, because if you take any element in G, then this is equal to n minus 1. Okay, hence this is also normal in G, and this completes the current solution. Then we have exercise 19, which is related to this one. Let G be as in exercise 18. Show in part A we have to show this. An n minus 1th power and an nth power, they commute. For all A and B belonging to G. Okay. And in part B we have to show this. N times n minus 1 is equal to E for all A and B in G. Just like the previous solution, here also they are just calculations. But I was thinking of something else. You see, in the previous exercise, we proved that Gn and Gn minus 1 are both normal subgroups in G. This idea came to me just now. Now, if one can show that their intersection is the trivial group, then because of the fact that they are normal, this will automatically follow from one of the exercises that we solved. Do you remember that if you have two normal subgroups n and m in a group such that their intersection is the trivial group, then the elements in n and m commute, where n is any element in n and m is any element in m. Here an minus 1 is an element in this normal subgroup and bn is an element in this normal subgroup. So if in that way also this can be solved, then one needs to show that this intersection is trivial. I cannot immediately see how one can show this, or even if this is even true or not. You try it, okay? You try to show or try to ascertain whether this is the case. If this is the case, then the solution will be quite neat. Okay, we can refer to that exercise and the solution will be immediate. However, that's not how we have done it here. Here we have done calculation. Will this be possible? For this, you say you take an element that is here as well as here. That means it's an nth power as well as it's some n minus 1 power. From that, if you can somehow conclude that both of them should be equal to identity, then our job will be over. But I doubt it will be the case. Anyway, let's continue with the solution. So the calculation is this. A(n) Bn minus 1 is equal to A inverse A. No, what am I writing? Let us start with A(n) minus 1 and Bn. Yeah, because that's what we have. So here we have A(n), Bn. Here we have applied one of the rules of exponent and associative law. And now, because of the hypothesis that continues to be true here, because we are dealing with the same group that we were dealing with in exercise 18. So we can write AB whole to the power n, which again then can be written as A inverse AB to the power n minus 1. Now in this part, A inverse and A will cancel out and we will be left with B. Along with that, note that in the solution to the previous exercise, we have already seen that this power is actually equal to B to the power n minus 1, A to the power n minus 1. Namely, we have seen it here, see, the order changes. Combining these two, you get B to the power n, A to the power n minus 1. So these two things commute. This calculation is also not very long. Just like that. In part B, we have AB, A inverse, B inverse to the power this. So this becomes equal to, we keep A, B, A inverse together and write B inverse separately. We take its nth power and then outside we take to the power n minus 1. Okay, so this can then be simplified like this, keeping in mind that the hypotheses are still true that we had in G. We are still in that G. This will be A, B to the power n, A inverse, B to the power minus n, to the power n minus 1. Now, let us now interpret this product as a product of these two elements. So here the n minus 1 will get distributed over the factors, but the order will change according to what we have seen so far. Then again, this one is minus 1. So this is equal to minus n. Here we have written b to the power n inverse just to show you that here the structure is like that. Some element times some other element times the inverse of this element. So the exponent comes here inside in the middle. Okay, then after this oh yes, now see, you can consider these two things together, b to the power n, a inverse to the power n minus 1. Now you use part A where an nth power and an n minus 1th power commute. The elements, the bases we have now are b and a inverse. So you can write like this. Oh, here we have b to the power minus n. So b to the power n and b to the power minus n, they cancel out, and we have a to the power minus n minus 1 times a to the power n minus 1. So they finally give us E identity. Note that we have used the solution to exercise 18 as well as part A of this exercise above. Above means in this calculation. So this completes the current solution. Two more are there. Let's complete this exercise set. Let G be a group such that AB to the power P is A to the power P times B to the power P for all A and B in G. And P is a prime number, where P is a prime number. Let S be the set of all elements X in G such that x to the power p to the power m is equal to identity for some positive integer m depending on x. That is, we are going to choose those elements for which such a power becomes equal to identity, where this m is determined by x. Then there are two parts. Proof. In part A, S is a normal subgroup of G. And in part B, if G bar is defined to be the quotient group of G by S, because once you prove S is normal, you can consider this quotient group, and if X bar belongs to G bar, where X bar is the coset of S. In fact, X bar is the coset of S, this coset of S, okay, Sx is such that its pth power is equal to the identity element E bar in G bar, which is the subgroup S. Then our original element x must be equal to E. So let us now solve this. Part A, one can prove by induction that AB to the power P to the power M is equal to A to the power P to the power M times B to the power P to the power M for all A and B in G and all positive integers M. The hypothesis which you can see is the case when m is equal to 1. It is given in our group, this happens. The hypothesis forms a basis for this induction. This proof by induction is actually quite straightforward, so I leave this one to you. Now with this at our disposal, we shall show that S is a subgroup of G, and then we will prove that S is normal in G. Let X and Y be two elements in S. then x to the power p to the power m is equal to identity, and y to the power p to the power n is equal to identity for some positive integers m and n. Okay, then xy to the power p to the power m plus n, by this identity this will be equal to x to the power p to the power m plus n times y to the power p to the power m plus n, and by one of the rules of exponent this is equal to x to the power p to the power m to the power p to the power n and y to the power p to the power n times p to the power to the power p to the power m. This is equal to E. Since m and n are positive integers, so m plus n is also a positive integer. Since m plus n is a positive integer, we have xy belonging to S. Okay. Also, x inverse to the power p to the power m by the rule of exponent, this is the inverse of this, which is equal to the inverse of identity, that is equal to identity. This implies x inverse belongs to S. Thus, S is a subgroup of G. Next, we show that S is normal in G. But let's first feed this some ink. Next, let G belong to G. Then Gx inverse, you can almost understand how the calculation is going to be. Which implies S is normal in G. So this completes part A. Now for part B, let x bar be the coset Sx in G bar such that E bar, then what is x bar to the power p? Sx to the power p. And what is E bar? E bar is S, or Sx to the power p is equal to S, or x to the power p belongs to S. That's because S is a subgroup. So not only are we having implies, but we have double implication. Okay, these things are equivalent. Now since x to the power p belongs to S, so x to the power p whole to the power p to the power something will be equal to E. So p to the power k is equal to E by the definition of S for some here we have written in the question, we have written x equal to E. No, x is not equal to E. X bar is equal to E bar. Please correct that. In part B, in the final conclusion, you write x bar equal to E bar. Okay, but I wrote there, that is wrong. You write this. You supply bars for some positive integer k, but then since k is a positive integer, so k plus 1 is also a positive integer. So from this final equation, you can conclude that x itself belongs to S. Hence, x bar, which is Sx, is equal to S, which is E bar. That's what we wanted to prove. And finally, we have this exercise on matrices. Matrix exercises are accompanied with hash. Maybe because the hash symbol is available. I mean, when you see this thing, the exercise assumes that we already know about matrices. At least we have some rudimentary knowledge of matrices and their addition and multiplication, those things. Okay, well, I think I have already talked about this, but let's just stress it once more. Why hash? My guess is that the hash symbol is already available, and the hash also in a sense shows a table, although a slant table, but this is the only symbol of that type. it shows a table where you have rows and columns. I think maybe that's why it's being used for exercises that need prior knowledge of matrices. It's only a guess. Let G be the multiplicative group of all real 2 by 2 matrices of this form A, B, 0, D, where of course AD is not equal to 0 because that is the determinant. Let N be the set of matrices in this group of this yet more special form. These matrices are also here because the matrices have the same form and 1 times 1 is 1, which is not equal to 0. Prove that part A, N is a normal subgroup of G. And part B, the quotient group G by N is abelian. Now the fact that N is a subgroup of G, this already has been seen in example 248. That N is a subgroup of G. We now show that it's normal in G. Let A, B, 0, D, this belong to G, and 1C 0, 1, this belongs to N. Then we calculate this product. Gn G inverse. A plus 0 A, AC plus B, 0 plus 0 0, 0 plus D, D. Okay, to calculate the inverse, determinant is AD, so D divided by AD is 1 over A. A divided by AD is 1 over D. Minus 0 by AD is 0 and minus B by AD is minus B divided by AD. So this is the inverse. Now we make the final multiplication. This times this is 1. This will if I multiply a with this one, a will cancel out and we have minus b by d, and then if I multiply this one with this one, that minus b by d and plus b by d, they will cancel out and we will be left with ac divided by d. Yes, 0 plus 0 0, 0 plus d by d 1. So this again is such a matrix, so this will belong to n. Thus n is normal in G. Finally, we come to part B, where we want to show that the quotient group is abelian. Let A1 B1 0 D1 and A2 B2 0 D2 belong to G. To prove that G by N is abelian, we need to prove that, note that we are trying to show that G by N is abelian. That does not mean we have to show that these two matrices commute. No, the cosets formed by these matrices commute. That is, we have to prove this. This is one coset and this is the other coset. We have to show that this is equal to another such product where we reverse the order. Or equivalently, we have to prove this. In A1 A2 A1 B2 plus B1 D2 this will be 0 and this will be D1 D2. We have to show that this is equal to n A2 A1 A2 B1 plus B2 D1 0 D2 B1. Note that we are not doing anything, we are just changing the thing that we have to prove into some equivalent statements. Or equivalently, that A1 A2 A1 B2 plus B1 D2 times A2 A1 A2 B1 plus b2 d shall I have space? Let me write it this part more carefully. a2 b1 plus b2 d1 0 d2 d1 inverse. This should belong to n. We need to prove this. So that's what we are going to do exactly. Now a1 a2 a1 b2 plus b1 d2 0 d1 d2 a2 a1 a2 b1 plus b2 d1 0 d2 d1 inverse. Okay, now to save our labor, we are going to, if you want you can do this also. The inverse will be this. That is, if you want you can write all these things minus a2 b1 plus b2 d1, this is 2 b2 d, the space is very small, b2 d1 divided by a1 a2 d1 d2. Now the first, this of course is 0, the first one will be 1, and then the first row second column entry will be somewhat quite complicated, but we need not bother, it will be something, no? The second row first column entry will be 0 times this plus this times 0 0, and the second row second column entry is 1. The only thing we are interested in is in the structure of this matrix, not all the elements. These two elements are 1 and this one is 0, so this belongs to n, where star denotes the appropriate entry. So that's it, that's what we wanted to show. This product, that is this matrix times this matrix inverse, is in n. So that means equivalently this is true, equivalently this is true. So G by n is abelian. This completes the solution, it completes the present set of exercises also, and it completes this section. After this, in the next video, we will start the new section, which is on homomorphism between groups. So that will be all for tonight. Okay, let me. No, I thought of telling you about something else, but we will discuss it afterwards. So that's it. I am signing off. This is me, Lucifer, from a mathematical room. Have a nice night.